This is the Math 217 lecture on the logic of hypothesis testing. We've seen a number of examples of hypothesis testing, and now I want to delve a little bit more deeply into what exactly it's telling you, and in particular what the significance level is telling you. So remember, and when we first talked about hypothesis testing, we observed that there are two different ways to be wrong, and they tend to have dramatically different consequences. They don't have very dramatic names, unfortunately. Their names are type 1 error and type 2 error. A type 1 error is finding significant evidence when the null hypothesis is true. Remember, you're finding significant evidence for the alternate hypothesis, so you are effectively believing the alternate hypothesis when it's false. A type 2 error is not finding significant evidence when the alternate hypothesis is true. So here, you're effectively believing the null hypothesis, continuing to believe the null hypothesis even though the alternate hypothesis is true. So here's the table, and the important thing to keep straight is that there's two separate things going on. There's whether or not the hypothesis is true. There's what's actually true about the parameters, which is a sort of universal Platonic fact that we don't know, but it's either true or false. And then there's the results of our particular test, what our sample tells us, and whether our hypothesis testing process concludes that that's significant evidence or not. Those are two correlated things, of course, but they're not the same thing. So either the null hypothesis can be true or the alternate hypothesis can be true. You recognize that in some situations there is a third possibility which we are not going to think about for now. And either you can find significant evidence or you can fail to find significant evidence. So if the alternate hypothesis is true and you find significant evidence, you're correct. If it's not, if the alternate hypothesis is true and you don't find significant evidence, that's a type 2 error. That's failure to be convinced when you should be. If the null hypothesis is true, if there's nothing going on and you find evidence that convinces you, you've made a type 1 error. And then, of course, if there's nothing going on and you don't think there's anything going on. If the null hypothesis is true and you do not find significant evidence, then again, you're correct. Let's think about what these look like in two of the examples I talked about earlier that I said would be helpful pictures to have in mind. The first is a courtroom trial. So the null hypothesis here, the default assumption, the thing you're going to assume in the absence of evidence otherwise, is innocent, that the person is innocent, and the thing you're assessing the evidence for is that they're guilty. So it's perfectly natural to view innocent as the null hypothesis and guilty as the alternate hypothesis. And in a trial, you're assessing the strength of the evidence. If there is sufficient evidence that the person is guilty, you convict them. And if you fail to find significant evidence, they're not guilty. They're set free. And notice the logic here is exactly the logic of a hypothesis test. If there isn't enough evidence either way, it's not that we found evidence that convinced us the person is innocent. If we fail to find evidence that they're guilty, we set them free. We treat it the same as if we found incontrovertible evidence that they were innocent. That's exactly what happens with a hypothesis test. So that means that a type 2 error is setting free a guilty person, and a type 1 error is convicting an innocent person. And of course, convicting a guilty person or setting free an innocent person is not a mistake. So there are two ways to be correct and two ways to be incorrect, and notice they have very different consequences. In this case, people generally agree that convicting an innocent person is a way worse mistake than setting free a guilty. So the standard quote from maybe it's Chief Justice Learned Hand or something like that is, better to set free 1,000 guilty people than to convict one innocent man. So that gives you a sense of the relative weight of those two mistakes. In contrast, other thing we talked about was testing blood for an HIV infection. Somebody donates blood, you're testing it to see whether it has HIV. If you find evidence that it has HIV. So you're literally looking to see if you find the antibodies to HIV in the blood, then it tests positive, we say, and if you don't find evidence, it tests negative. So here the alternate hypothesis is that the blood is infected, and the null hypothesis is that it's uninfected. It's the default assumption. Once again, two ways to be correct. You can throw out bad blood, or you can keep good blood. Two ways to be incorrect. If the blood is infected and you don't find significant evidence, that's what's called a false negative. If the blood is clean and you find significant evidence, that's called a false positive. That's a type 1 error. False negative is type 2. Throughout medicine, the language of false positive and false negative, when you find evidence for a condition that's not there, or you fail to find evidence for a condition that is there, is used instead of type 1 and type 2. Frankly, it's a more helpful notation, terminology, but it's only used in medicine. And notice here that the roles are kind of reversed. The terrible mistake is a type 2 error here. Why? Because you've got infected blood that you failed to notice infected, so you let it through. And many people can get infected. Whereas a false positive means there's a good pint of blood, you test, and you find that it's tainted, so you throw it out. You've lost a pint of blood. A shame, but nowhere near as terrible as infecting a bunch of people with a permanent disease. So one of the things you get from that example is that the consequences of the two different types of error, type 1 and type 2, are dramatically different. And I hope that you understand there's a trade-off there. There's a trade-off because if you have a high standard of evidence, if you require a lot of evidence before you're convinced of the alternate hypothesis, that's what we would, in the high standard is described in the courtroom setting as proof beyond a reasonable shadow of a doubt. To convict someone, you need to have uncontrovertible evidence. That's a high standard of evidence. That means you'll rarely have type 1 errors, right? You'll rarely convict an innocent person because you're only going to convict them if you're certain that they're guilty. On the other hand, if you have a high standard of evidence, you'll have a lot of type 2 errors. You will set free a lot of guilty people they're guilty, but you just don't quite have enough evidence to prove that beyond a shadow of a doubt. So that's a good thing in a courtroom setting. A high standard of evidence means you very rarely do the terrible thing of convicting an innocent person, and you accept that maybe more often than you'd like you set free guilty people. That's how our jury system is set up, and people generally accept that that's a good thing. That would be a terrible thing for the HIV. If you were only threw out blood, if you were absolutely convinced it was bad, you'd be letting through a lot of bad blood, causing lots of disease. So what you need there is a low standard of evidence. The sort of cheeky phrase is, when in doubt, throw it out. If there's any chance that this blood is tainted, you should throw it away. You should assume that it's guilty until proven innocent. So a low standard of evidence means you have lots of type 1 errors. Lots of times, random variation will trigger whatever the test signal is. It will think it's seeing the antibody and say, oh, this is bad, and you'll throw out perfectly good blood. But you will have few type 2 errors, which is setting free the guilty or false negatives, because it's relatively easy to be convinced that the blood is bad, that the person is guilty. So what I want you to understand here, the most fundamental thing, is your standard of evidence, what your cutoff for how convincing the evidence has to be before you believe it, is a decision about the trade-off between type 1 and type 2 errors. You can't control, in some sense, the total number of errors, but you can control how much of them are type 1 and how much of them are type 2. You can think of your standard of evidence as a dial you set. That reflects the relative importance of type 1 and type 2 errors. Courtroom trial, you set it at one setting because type 1 errors are terrible. HIV blood test, you set it at a much lower standard because type 2 errors are terrible. So that the significance level is that dial. It is your standard of evidence. The lower the significance level, the more evidence, the stronger the evidence has to be before you find significant evidence. Okay? So all of this is to say that that the courtroom trial of standard of proof beyond a reasonable shadow of a doubt corresponds to some very, very low significance level, and the blood testing standard of when in doubt, throw it out, corresponds to a very high significance level. Just to review that, low significance level corresponds to a high standard of proof, and a high significance level to a low standard of proof. So that means the low significance level, like the courtroom trial, has few type 1 errors, whereas the high significance HIV situation has many type 1 errors, but the trade-off is that the courtroom trial, low significance, has many type 2 errors, whereas the high significance has few type 2 errors. So that's the first fact that you need to get out of this lecture. The significance level is controlling the standard of evidence, which is controlling a trade-off between type 1 and type 2 errors. And that's why you set your significance level based on what your situation, the relative dangers of type 1 and type 2 errors. But the significance level has a precise interpretation in terms of that. So if you do a significance test at the alpha significance level when the null hypothesis is true, so we're making one of these Monty Hall statements where you're imagining that you know, like you're looking down from heaven, you know that the null hypothesis is true. You're watching somebody who doesn't do a hypothesis test. If you do a significance test when the null hypothesis is true, then your chance of finding significant evidence is alpha. That is, your chance of making a type 1 error is alpha. So the basic sentence, most important thing to walk away from in this lecture is the significance level alpha is the chance of making a type 1 error when the null hypothesis is true. Why? Because your significance level is saying what's the biggest p-value I'll consider significant. So if you're testing at the 1% significance level, you're saying I'm going to be convinced if the p-value is 1%, what's that 1%? That's the chance that you would get such a little p-value. Chance that you'd have this much evidence if the null hypothesis were true. So you get a p-value of 1% or less 1% of the time. Okay, so if your significance level, which is your standard of evidence in trial, is 1%, this guarantees that 1% of innocent people who come before the court will be falsely convicted. That sounds like a pretty high significance level for a courtroom trial. So you could lower it. Maybe you'd make your alpha 0.001, and that would guarantee only 1 out of every 100,000 innocent people would be falsely convicted. But that would increase the number of guilty people who are set free. And now the logic of formal hypothesis testing has a consequence that while you can always know your chance of making a type 1 error when the null hypothesis is true, you can essentially never calculate your chance of making a type 2 error when the null hypothesis is not true, when the alternate hypothesis is true. And that's essentially because the alternate hypothesis is imprecise. It could be slightly true. If the alternate hypothesis is p is greater than 0.5, p could be a little bit greater than 0.5, in which case it's going to be easy to make a type 2 error. Or p could be way greater than 0.5, in which case it's going to be hard. So that is, anything you can say about your chance of making a type 2 error is a complicated calculation which uses a lot of assumptions beyond the realm of this course. Okay, and here is the most important consequence of that fact, that the significance level is the frequency with which you'll get a false positive when the null hypothesis is true. That means that if you do many tests at, say, the 5% significant level for effects that aren't there, you will get significant evidence anyway, 5% of the time, just by chance. And the following XKCD cartoon illustrates this point and illustrates why this leads to the biggest danger in hypothesis testing. I'm sure you can read it, but let me kind of give you a guided tour. Somebody believes that jelly beans cause acne, so the scientists have to stop playing Minecraft and start investigating it. And I want you to pay special attention to the second panel. It says, we found no link between jelly beans and acne, parentheses, p is greater than 0.05. That is a shorthand that is sometimes used in science. P means the p-value, and to say p is greater than 0.05 is saying we did a significance test at the 0.05 or 5% significance level. The p-value was greater, so we did not find significant evidence. So that's a shorthand for saying this data is not significant evidence that jelly beans are related to acne at the 5% significance level. Okay, so that's all set. But now the person says, oh, no, it's only certain colors that cause it. Now if you watch, they go through and they test 20 different colors. And where's the green? Sorry. There we go. And as they're going along, I guess they get to green. Sorry, I got myself muddled there. And green, they find significant evidence. So out of 20 colors, one of them they found significant evidence that is related to acne, and this is the newspaper report, green jelly beans linked to acne. The 95% confidence is not really a correct way of saying 5% significance level. They're related, but not quite the same. And it said only 5% chance that this could be a coincidence, which is absolutely correct about the particular study of green jelly beans. But of course they did 20 of those studies. So if none of them were related to acne, you would still find, that means the null hypothesis is true in all 20, so you would expect 1 out of 20 to get you significant evidence at the 5% level. In other words, what they found here is exactly what you would expect if there was no relationship between jelly beans and acne. But if you take that one success out of the context of all the failures, it looks like it's evidence for a relationship. Lest you think that that's an abstract point in a cartoon, scientists do hypothesis testing all the time, and of course it's the nature of journal articles that if you don't find an effect, nobody's going to publish it. So all the things where they don't find significant evidence are unpublished, and all the things where they do find significant evidence are published. So it may be that the things that are published represent 5% of all the things people try, and that we're just getting a lot of exactly the percentage of significant evidence we would expect when there's no effect going on. In other words, it may be that a lot of studies in journals that find significant evidence are false positives. The summary here of the moral, and we'll explore this more in class, is that fact that the significance level tells you the chance that this would have happened, chance that you would find significant evidence if the null hypothesis is true, only works if you decide what your question is before you look at the data. So here, if the question was, does some color, jelly bean, cause acne, then finding one significant situation out of 20 is not evidence for that at all. If you started out with the question, do green jelly beans cause acne, and only did that test, then getting 5% significance level would be significant. It's a kind of subtle point. The simple way to say it is, you decide the question that you're asking, the significance level, the alternate hypothesis, everything about what you're asking before you look at the data. And if you let the data tell you what question to ask, then you get all sorts of anomalous behavior, and that leads to most of the mistakes made in statistics in science. Okay, so here's the summary. After watching this lecture, you should be able to define type 1 and type 2 errors, and you should understand that, typo, the significance level is your chance of making a type 1 error. After processing this lecture, you should be able to interpret that says confidence interval, the significance level as a probabilistic statement, and understand the problem with common errors in the logic of hypothesis testing.